Hello, class. Welcome to what I believe will be the second to last video. I know that there's been a lot of stuff this week, but there's been a lot of cool stuff to show you, so hopefully you're enjoying all of these various examples we've been doing, and there will, of course, be more cool examples for you to look at in the homework. Okay. So today, I'm going to show you something that's really cool about generating functions, which is that sometimes you can just sort of do random algebra and find identities between things. So you don't even necessarily have to know what you're looking for. If you know the sorts of tricks we've been doing, you can just sort of happen upon true identities about partitions. So today, we're going to look at this particular kind of partition, which is partitions that have no part equal to 1. So I've gone ahead and just as an example so that we can get up to starting this, I've listed all of the partitions of 5 and 6, and then I've circled the ones that have no part equal to 1. I'm going to call this z of n, not because that's standard, but just because we only have so many letters, and I haven't used z yet. So z of 5 is 2. Z of 6 is 4. And we want to see what we can figure out by thinking about the generating function of z. Okay, so I'm going to call that generating function capital Z. So capital Z of x, that's going to be my sum as n goes from 0 to infinity of little z of n times x to the n. And we can figure out how this is going to work. So I can use any parts that aren't 1. So I can use 2's. Likewise, I can use 3's, 4's, and so on. So if I rewrite all of those things as the geometric series that they are using our formula, this will be 1 over 1 minus x squared times 1 over 1 minus x cubed times 1 over 1 minus x to the 4th times ... Now, if you remember our regular partition function, so this was this thing that got this sort of fancy-looking e because it's named after Euler. This was the sum as n goes from 0 to infinity of just p of n times x to the n. This was, if we worked it out, 1 over 1 minus x times 1 over 1 minus x squared times 1 over 1 minus x cubed, and so on. And I want to point out, this is not so different from the thing we just wrote down. Namely, the only difference between this z of x and this e of x is this term. And of course that makes sense, because what's the only difference here? Here I was allowed to use anything except 1. Well, here I'm allowed to use anything except 1, but I can also use 1. So I had to put in this additional term to compensate for the fact that I'm also allowed to use 1s in my partition. Okay. But that means that these two functions are actually very similar algebraically. Namely, if I want to look at z of x, well, z of x is very closely related to e of x. Namely, all I have to do to go from this e of x to z of x is cancel out this first term. So that is to say that z of x is in fact 1 minus x times e of x. Okay. Now, this seems not to say very much. And I mean, on some level, that's true. But I want to actually write all of this out super explicitly. So on the left-hand side, we've got the sum as n goes from 0 to infinity of little z of n times x to the n. And on the right-hand side, we have e of x minus x times e of x. So that's 1 minus x times the sum as n goes from 0 to infinity of p of n times x to the n. Okay, so let's continue this. So it's z of n times x to the n, and that's equal to... All right, so let's figure out what the coefficient of x to the n in this is going to be. So I could have gotten an x to the n in two ways. One is by multiplying a 1 by an x to the n. So we start here with a p of n. And the other way is to have started with an x to the n minus 1 and then multiplied by an x. So I fear I have not left myself enough room to write this in this big a font. So minus p of n minus 1 times x to the n. Okay, just to write that out more clearly so that this all works out. What I said there is that this works out to be p of n minus p of n minus 1 times x to the n. Okay, and again, just to repeat, where does this come from? This comes from thinking, what's the only way I'm going to get an x to the n over here? Well, there's two ways. One is to start with an x to the n and multiply it by 1, and that gives me the p of n. The other is to start with an x to the n minus 1 and then multiply it by x. And so what's in front of the x to the n minus 1? Well, p of n minus 1 is in front of that. Okay. But these two things, these two power series now, are equal. And so that means their coefficients in front of x to the n are equal. So this is equal to this. And so for free, just as a benefit of multiplying out some equations, we have proven the following theorem, which says that the number of partitions of n into parts that are not 1 is exactly the same as the number of partitions of n with no restriction minus the number of partitions of n minus 1 with no restriction. Okay, and so this is a theorem that we could prove combinatorially, and in fact, you should expect that that will show up on the homework. But we've proven it here again with basically no effort. We just sort of looked at some things and wrote them down and were like, oh, hey, this is true. Okay. So let's just look at this theorem that we just proved in this specific case, just to convince ourselves that it really works. Okay, so you can calculate here that p of 6, actually I'll use blue just so that you can see the new thing I'm writing. P of 6 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And p of 5 is 1, 2, 3, 4, 5, 6, 7. And so p of 6 minus p of 5 is 4. But that's also the same thing as z of 6, which we calculated to begin with, is 4. Okay, so this gives you some idea, again, of the power of generating functions. Okay, next lecture, which I intend currently to be the last one, we're going to prove an even more bizarre identity about partitions using generating functions. And then I'll talk a little more about some other things that you could prove by looking at these kinds of things. And then we'll be done for this week. But until next time, Stay well.